Right, this is 2013, number 6. It gives us a little data table up here. It gives us an empirical formula of 2 different compounds, but that empirical formula is the same. And then it gives us a list of their properties: solubility properties, boiling point properties. Boiling point is all intermolecular forces, so we know that's coming. Why do these things have the same empirical formula and different properties? It's because those are isomers of each other. So they have different structures even though they have the same elements making up those structures. And so that's what this first part is talking about. It's really just drawing up Lewis structures, which shouldn't be a big deal for us. It says complete the Lewis electron dot diagram of box X, including any lone non-bonding pairs. So we have these C2H6O sitting in this box. They've drawn the skeletal structure. We just have to include the bonds in there. I like to count up bonds, or sorry, electron pairs. And so we've got oxygen has 6. Each of those carbons has 4, so that's 4, 8 plus 6, 14. And then 6 more from the hydrogens gives us a total of 20 electrons, or 10 pairs of electrons. I think that's healthy every time. I start by sticking 1 pair in between each of those elements. You have to have at least 1 pair in between each of those elements to make that molecule work. And when I do that, I got 1, 2, 3, 4, 5, 6, 7, 8 total pairs. I need 2 more pairs to be in the drawing. Everything's filled its octet except for oxygen there, and so oxygen needs a couple more lone pairs of electrons sitting on it. There's our 10 pairs. Everything fits the octet rule. Those 2p elements, carbon and oxygen and nitrogen and fluorine, those guys have to have an octet of electrons. So if they don't, you've got something goofy in your drawing. But that's it on A part 1. You just have to fill in that structure. In A part 2, it says box Y, draw the isomer for the other compound, which is just a structural isomer. So when we look at this, box X, there's this tendency spatially for us to go, well, just put the oxygen on the other side. But if you put the oxygen on the other side, it's just looking at it flipped over, right? And these molecules can move in these 3-dimensional spaces. So we have to find a way for that oxygen not to just be bonded to 1 carbon. And the way this isomer works is we've got carbon bonded to that oxygen in the middle between those other carbons. That completely changes that structure, and those hydrogens get put off of those carbons just like this. There is our 8 pairs so far, and we need 10 pairs, still the same number of pairs, and so those lone pairs go on that oxygen sitting in the middle of that molecule. What's the difference in those? See that oxygen to the hydrogen here? Really electronegative element bonded to a hydrogen. That makes the connection between it and the next molecule contain hydrogen bonding, right? That's not a hydrogen bond, but the attraction to the next molecule over will be a hydrogen bond. Why is that important? Because we're talking about intermolecular forces. We already saw that with the boiling points. Is this one over here polar? The answer is yes. That guy's polar, but that guy doesn't have hydrogen bonds because this carbon has a lower electronegativity, and so there's not as big a pull from that carbon to that hydrogen. So will it attract other molecules? Yes. Is it slightly polar? Yes. That's why it's slightly soluble, but it doesn't have the hydrogen bonding. So we're going to have to explain that here in part B. So part B says, on the basis of the complete Lewis electron dot diagrams you drew in A, and the information in the data table, identify which compound, 1 or 2, is represented by X. So X is going to be the one that has the higher boiling point and the greater solubility. Why? Because it's more polar, because it has greater intermolecular forces, specifically hydrogen bonding. Now when we get down here, it talks about each compound, right? So we're going to have to explain intermolecular forces in each compound. So here we go. Box X is representing compound number 2. That's the answer to the question. So I'm going to answer that question. X represents compound 2. Answer the question. Because X has hydrogen bonding. Y only has dipole attractions. And we probably shouldn't write only there because dispersion forces are there, but I think you're okay. Only has dipole attractions. The hydrogen bonds are stronger. Intermolecular forces. And therefore X has a higher boiling point. Good, that's it. And you can, so that works fine. You can justify it through the boiling point up here, or you could also, either or, you could justify it through the solubility. You could say the hydrogen bonds in compound number 2 cause it to be more polar, and because it's more polar, it's more soluble in the polar water. That would be fine too. So you can justify it through boiling point or through solubility. Those would both be valid. That's part B. That's probably what it is, a 9-point question. You're up to 4 points. Point here, point for the correct identification of which compound, and then a point for the explanation in terms of their intermolecular forces. So you're up to 4. Then we get to the backside. This is a completely different set of data here. Stop bouncing thing. Completely different set of data. Totally unrelated to the first half. This gives us dichloromethane, CCl2H2, and carbon tetrachloride, CCl4. I'm not going to write those big names out in the thing. I'm going to put CCl2H2. And you should probably do the same. It'll save you a little bit of time. Dichloromethane has greater solubility in water than carbon tetrachloride has. Account for the observation in terms of intermolecular forces between each. Again, we're dealing with boiling points and vapor pressures here. When we look at boiling points, the lower the boiling point, the more of it's turning into vapor, and so we have a higher vapor pressure is how that works. Higher boiling point, stronger intermolecular forces, lower vapor pressure. This first part, and we have to be careful here, this first part is in terms of their interaction with water, and that's an important piece of this as we go. So we're talking about solubility here in water, and so when we look at those two, dichloromethane, we've got to talk about intermolecular forces between each. So dichloromethane in part C, the CH2Cl2 is polar. So it has dipole forces between itself and water. And therefore is soluble in water. Carbon tetrachloride, on the other hand, is nonpolar. Good. It only has London dispersion forces by itself, and so the forces between it and water, when we look at CCl4, has dipole-induced dipole, right? Is it nonpolar? Yes. So why is it dipole-induced dipole? It's because when that water molecule comes over, it attracts the electrons away from one side of the molecule, and so it induces a dipole in CCl4. So this is dipole-induced dipole attractions between itself and water. The dipole induced dipole forces are weaker. I'm going to put are less polar. I'm going to put are weaker. And therefore CCl4 is less soluble in water, right? That's all about the interaction between those and water. Because question D, part D, looks really similar in the type of question they're asking. Because part D comes back and says, why do they have a higher vapor pressure? Why does dichloromethane have a higher vapor pressure than carbon tetrachloride? That's talking about the intermolecular forces just between this and itself. And so these dipole forces here happen to be weaker than the London dispersion forces between CCl4 and another CCl4. Because there's so many more electrons here, so much more polarizability with those London dispersion forces. And so this is the one I hate. I hate that they make polar things have lower boiling points, and they didn't make them. This is actually how this works, right? But I hate them asking it because it's there to confuse people. Because this is polar and this is non-polar, we think this should have weaker intermolecular forces, but it has so many more electrons here. And so, in part D, again, we've got to talk about their intermolecular forces. Part D, CCl, let's do it the same way. CH2Cl2 has dipole and dispersion forces. But CCl4 has greater intermolecular forces with just the dispersion forces, and therefore has less vapor pressure. That's tough, the difference between those in the midst, because it's a small difference, but difference nonetheless. And then our last one on E says they give us an electron dot diagram of methanol shown below. Molecules of methanol can form hydrogen bonds with water. In the molecule below, draw a water molecule in a correct orientation to illustrate hydrogen bond between a molecule of water and the molecule of methanol. And so for a hydrogen bond, we've got to have that water molecule where the hydrogen, the positive side of a water molecule, is attracted to that super electronegative oxygen. I would label it. I would put that's my hydrogen bond there so they knew. You could do the same thing on the other side. You could have oxygen with its hydrogens this way. Oxygen has that negative side of its molecule. You could draw that line between there and the hydrogen. It only wants one. That's the one that the key gave, but they would take it. Same kind of deal here or off of this guy. Either one of those would be valid. And you pick up a point there at the end. That's number six on 2013. Have a good day.